All right, so let's repeat the definition of remote sensing. So what we're going to focus on over the next few lectures. Remote sensing is collecting data without directly measuring the object. So, in short, any medium or any instrument that you're using which does not touch the object that you're measuring or the object that you want to from which for which you want to collect some data. So any medium or any instrument that does that is a remote sensor. That's how we call it. Our eyes are remote sensors. But for example, a ruler, which we use to measure um, uh, a square that we draw on a piece of paper, is not, because the ruler is going to directly measure the object. We also started talking about a certain type of remote sensing imagery. In this lecture, in this course, we particularly focus on imagery that is that shows the geographic areas, but remote sensing can be used for other purposes. For example, collecting data through Hubble telescope. That's also remote sensing, right? We don't measure all those galaxies. We essentially take pictures and then use those pictures to learn something about those faraway lands or faraway galaxies. And also, remote sensing is being used to take photographs of planetary objects. Like the probably 2 years ago, we had the New Horizon mission, and it flew by Pluto, and you've probably seen those photos of the heart on Pluto. It's kind of an interesting, probably some sort of a plane that actually has this heart-like shape. If you haven't seen that, Google it. It's really cool. But we focus here obviously on geographic areas, or on the Earth, on taking photographs of the Earth's surface, and they are taken top down from high altitudes. The major instrument that we use is a camera. And here you have a diagram that shows a camera, and you have an object that's obviously an apple. And so what happens here? Well, some source of energy, like sunlight or energy from a light bulb, is emitted. It bounces from the object. In this case, that's going to be an apple. And then that reflected energy is being registered by the device, by the camera. So there is lens here that collect this reflected energy, and then that's collected energy, those rays, pass through onto the camera sensor right here. All right. And that's being recorded on some medium like film. What type of applications are there for aerial photographs? Or apart from the scientific ones, of course, I am a scientist, so I'm biased towards using aerial photography to study geographic regions. Other sciences also use aerial photography. For example, aerial photography is very commonly used in archaeology. right here you have an image of a site in United Kingdom, which probably shows prehistoric settlements remains. You wouldn't see that from above, but it's pretty easy to see all those patterns, which are usually very subtle on the ground from the airplane. We also use aerial photographs to evaluate spread of fire, very common use, especially when we have large-scale wildfires, like the wildfires we have on a regular basis these days yearly in California, to evaluate the extent of flooding. That is something you're going to do as the last exercise. The after effect of Hurricane Katrina, and other disciplines. I'm going to show you a video in a moment where at the end of the video you have a lot of practical applications of aerial photography, applications that do not necessarily relate to scientific research, but applications that are actually useful for a variety of businesses. How do we capture the image? Well, you would probably think about the airplane as the major source, and you're not wrong. That historically was the go-to instrument, i.e. mounted camera, camera mounted to an airplane, but it's very expensive. And these days we use drones more and more commonly. The video is going to talk about drones as the source of aerial photography, but there are other sources. You can use towers, kites, balloons. Here you have Willis Tower in Chicago. I don't know if you've ever been to Willis Tower. It's essentially a balcony which is built completely from glass, and if you have fear of height, I strongly discourage you from standing on that balcony, because you really feel like you're gonna fall if you look down, right? You can see everything through the glass surface. Now, how does it look from above? So I just talked about the camera itself, but the collection obviously is from certain altitude. In the past, we use films, so there was a certain area covered by the camera from above, and whatever was captured by the camera was recorded on an image. And if you're more familiar with how images were created, essentially there was a chemical reaction happening on the surface of the image in response to the exposure to light. These days we do not use films anymore. We use digital cameras, or essentially we record the data directly in the form of digits or bits and bytes, just like the digital cameras we use in our cell phones. So there's not really much of a difference. Again, there's a certain area that's being covered by the camera. The lens collect the reflected light, but on top of just registering the photograph, there's also filtration. The filtration means that we split whatever light is being reflected into certain bands. I'm going to talk about bands when we cover remote sensing. For now, I would just want you to remember that the data that we see or the visible light is usually a collection of 3 different bands or chunks of the visible light spectrum. We have blue, green, and red chunk, and then they are combined together to give us a true photograph. The cameras that are mounted on airplanes usually collect also near infrared imagery. That is imagery that's close to the red band, but something that we cannot see anymore. That's why it's called near infrared. Also, another important thing is that the data is collected as a matrix as a matrix array. So we collect the data using squares that are then combined into a matrix or mosaicked. Okay, so we went through the data collection, the photograph. Now what are we going to register? Well, as I said, most of the imagery these days, the vast majority, is digital imagery. So essentially what we record is we record brightness value of pixels. So an aerial photograph is like any other photograph. It's composed of pixels. Pixels are like cells in the raster data model. There is no difference here. We just call them pixels because that's the term used in photography. And if you zoom in to any photograph very, very much, I mean, you're really going to zoom in to a level where you can see those pixels. In black and white, you will see that each of those pixels has a certain brightness value, and the brightness value is a range from black to white through different shades of gray. The most common image that we record is an 8-bit image. And 8-bit means that it has, as the name suggests, it's composed of 8 bits. A bit is a chunk of information used by computers that has only 2 values, 0 or 1. So if you have 8-bit image, you can have 2 to the power of 8 combinations of zeros and ones. That gives you 256 levels of gray, from black, which is represented by value 0, to white, which is represented by value 255. I'm going to show you later on another video which is going to talk much more about bits and bytes and how they relate to photography. This is just an overview. So in this example, you have an area photograph and you have a teeny tiny area zoomed in. You can see that there are certain pixels with certain levels of brightness or value of brightness. And in the background, what you really have is numbers that are associated with certain brightness value. That's just like when we talked about the raster data model, I showed you those schematic maps where you had different land uses, different colors. I believe it was red, green, and yellow. And then I also showed you that map using values. That's how it's being stored. It's being stored as values. Actually, to be precise, when it's stored in a computer, you don't really have those numbers. You have combinations of zeros and ones, but they translate to values from 0 to 255 in the decimal system. More on that. I know it's a lot of information, but there's going to be a lot of that explained later. Oh, here you have another example. This time it's a false color image, another topic to cover later, and it's a geologic map for a portion of Austin, Texas. And as you can see, if you zoom in, you will see those cells. We call them pixels. This is actually a composite image. A composite image is an image that is composed of multiple bands. If you go back to this example, a composite image would be an image that, for example, merges those three bands together, and that's why it's colorful, because we can then assign certain colors to certain bands. But the rule behind it is the same. Each of those pixels, which an associated color, is actually a number that represents a certain shade of a certain color. More on that later. Unfortunately, when you fly over an area, either in an airplane, or you use a drone for that, or a balloon, or a kite, it's never perfectly aligned vertically. All right, so there's always going to be some sort of a tilt with small angle or even much higher angle. We actually divide, and that's called perspective. So that we have different perspectives of collecting aerial photographs. The vertical is the one that we really strive for, but usually we end up with a tilted photo. That's a photo where we are a little bit off from the vertical view. Then we also have oblique photographs. They are sometimes done on purpose because we want to see a perspective view rather than a top-down view. And oblique are essentially photographs that are taken at a certain angle of a landscape. Now, this is not the same as tilted, because tilted are something we get, we don't really want to have. In terms of oblique imagery, this is a certain type of imagery that is being collected for purpose. As I said, to get a certain perspective of the landscape, sort of like a three-dimensional perspective. And then we have high oblique view. Again, it's taken at a certain angle of a landscape, but with high oblique view, we take the photograph so that we actually can see the horizon. And here you have an example. This is the view of Michigan Capitol. You have the vertical view, the ideal, so to speak. Then you have an oblique view. You can see now, like, you have this three-dimensional perspective. You can see sides of the building rather than just the outline of the blueprint. And high oblique view, where you can see the horizon.